In this video, we're going to look at our first method of solving systems of equations, which is by graphing. Now, the equations that we're going to be solving are linear equations, so we are going to be able to graph these in the coordinate plane using everything we just learned in Unit 4. So first, what is exactly a system of equations? Well, it's a collection of two or more equations that have the same set of unknowns, or the same set of variables. So we'll have typically two equations that are both written using x and y, and our goal is to find the values of x and y that work for each equation in the system. So when I plug in the values of x and y, I get true statements both times. We're going to focus the majority of our time on systems of two equations, but we will take a day to look at what happens when we have three equations combined in a system. When we talk about the solution to a system graphically, that's going to be the intersection of the two equations of the two lines, because at that intersection point, both those equations are satisfied by the same values. So we have three different types of systems that we could come across. The first is these lines here in blue, which is where we have one intersection point. One intersection point means that we have one solution. We have some vocabulary that we're going to introduce here. That is independent and consistent. So an independent system is a system that has exactly one solution. It's an independent solution that stands by itself. The system is consistent because it has a solution. Our second example here, it looks like one line, but it's actually two that are overlapped on top of each other. That's basically saying that they're the same line. So here we have infinitely many solutions, because as that line continues in both directions, it continues to overlap. That line has an infinite length, so we have infinitely many solutions to the system. This is also a consistent system because there are solutions, but this is a dependent system because all the points that work in one solution also work in the other equation. The solution value of x depends on the solution value of y, and vice versa. Finally, we have these two lines here, which, as we can see, both have the same slope, and which we now know means that those lines are parallel. Since when we talk about a solution, we're talking about the intersection, parallel lines never intersect, so parallel lines in a system don't have any solutions. This is an inconsistent system because it doesn't have any values that work for both equations. And when we say that a system is inconsistent, we're not going to use either of these dependent or independent terms. Alright, so basically all we're going to do is graph the lines and look for the solution. And we'll talk about how we identify our solution once we've got our lines graphed. So first we have x equals 4, we'll do that in red, where that's a vertical line with an undefined slope where all of the points have an x-coordinate of 4. So I'll do my best to get that straight here. So we've got our first line. And then we want to graph our second line. We have a y-intercept of -4 and a slope of 1/2. So we can plot all those points. And we can see that those lines do very clearly intersect. And again, you just want to make sure you graph as accurately as you can because you are looking for that intersection point. So here we intersect at the point 4, -2, so that's our solution. And that's how we're going to write it. We're always going to write this as an ordered pair. Because we have a solution, this is a consistent system. And because we just have one solution by itself, this is an independent system. Go ahead and pause the video, graph the second system, and see if you can figure out the solution. Alright, so if we graph each of these lines, since they're both in slope-intercept form, if we look at them right away, we notice that they have different slopes. Oh, my mouse disappeared. So we know that they are going to intersect at some point. We can fill that fairly easily. And if we look at this, we'll see that our solution is at the point -3, 4. So that's our solution. And again, since we do have a solution, this is a consistent system. And since, again, we just have one solution by itself, this is an independent system. Now, of course, we're not always going to give you equations that are nice and organized in slope-intercept form. So sometimes we're going to have to do a little bit of work first in order to graph. Go ahead, pause the video, see if you can get the first set of equations into graphable form, and then see what they look like on the coordinate plane. Alright, if we look at this one, we end up with two lines with the same slope. But again, we're asked to solve by graphing, so we need to make sure that we actually show the graph. And we can see that those lines are parallel, they're not going to intersect. So this is an inconsistent system, and we don't pick independent or dependent. Here we're just going to put no solution. We can also write our no solution symbol there. Alright. Now, if we got no solution in this one, chances are we may get infinitely many solutions here, but we still want to check it out, see what's going on. So we can go ahead and start to reduce. So we can add 12 to both sides and see what we end up with. We divide by 3, and we'll get negative 6x plus 4. So we can go ahead and graph that equation here. We only got 2 points that are going to fit. We've got that one there. And now we can go ahead and reorganize our second equation. We don't want that pen, this one. So we can add 6x to both sides. Oops, sorry, not add 6x. We don't want to do that. Take that back. We can add 4 to both sides. And we get the same equation. So we just tag that on there. You want to make sure you draw both lines so we can see that they're both there together. So that means that you want to make sure that you have arrows for both lines as well. And I know it can be kind of tricky to draw with just your pencil to show 2 lines on top of each other. So just put one set of arrows a little bit shorter in than the other set, and that's good enough to show it out. We have solutions. This is a consistent system. And now, since we have infinitely many, this is a dependent solution. Here we have to say infinitely many solutions. We may also write IMS. What we cannot say is all reals or all real numbers. That's actually no longer allowed to be used for systems because it's not true that all real numbers work. If I pick 2 for my x-coordinate, there's very specific values that I have to pick for my y-coordinate. I can't just pick any real number that I want. So because of that, we just say there are infinitely many solutions that exist.